Swayam Prabha. Digital India. Educated India.
So let's continue with our lecture on this GEN's course of its modeling and simulations of granular material. And so today I'm going to touch upon this topic, uncoupled CFD-DEM modeling for geohazard and additive manufacturing here. So I will split my lecture into two parts. And first, focus on how we simulate geohazard like debris flow. And the second part is modeling the additive manufacturing. But essentially, we want to use the same methodology. It's coupled computational fluid dynamics with discrete element method here. Okay, so first part is the geohazard part. I guess that debris flow is this is a debris flow happening in Japan. I think last week, a couple of weeks ago, and we read the news that a terrible debris flow that hit a village in India as well. So debris flow is everywhere, I guess. So the lectures that organized into this four part. First, and then we model debris flow by unresolved CFD-DEM, and then we introduce different coupling schemes of CFD-DEM and for all kind of different diversified need. And the third part is how we demonstrate how we can really perform high fidelity simulations of laser powered bed fusion for additive manufacturing. And then I will conclude my lecture for today. And the first one is the debris flow and the mitigation, how we can really understand the problem, how we can model the problem here. Okay, and then this figure shows one of the major debris flow events that caused a black rainfall happening in Hong Kong back in 28, and then indeed last week, 2 weeks ago, there's also a historical record of black rainfall happened in Hong Kong and caused other debris flow event. So debris flow indeed is one of the major natural hazards for Hong Kong. I guess that is also in many other places around the world here. Okay, and it caused a huge property damage as well as human life losses. And then this is another satellite image taken by the digital globe, and then for a Zhouqi debris flow happened in China back in 2010, and then that one basically killed 1,500 more than 1,500 people here. Okay, and so that's as you can tell that how debris flow as a major type of geohazard can be so fatal here, right? And then let's see that what exactly is debris flow and see a close look. And this is a debris flow recorded by camera, and it happened in Switzerland here. And then, let's see that how debris flow is different than the flood and under like avalanche, rock avalanche here. Okay, you can tell from this video, it's a highly mobile, multi-phase, multi-scale mixture, and dominated by so-called interparticle interface, means the liquid phase and the particle phase. Intraphase means that the debris particle itself can really have friction and rolling over each other, and so this is called an interface here. And phase based between this debris and this natural gully in the so that will change their mobility quite a lot. Yeah. Okay. And so when we look at this distinguished feature of debit flow, and then indeed these features pose great challenges for numerical modeling here. The major challenge, first challenge is we need to consider a massive debit particle and a particle fluid interaction, and that indeed this interaction is dominant over the different intuitional phenomena we observe in debit flow, like a surge flow, surge waves, boundary flow, that show here. This is a typical boundary flow. And also if the confluent with other flow, like there's a other flooding and existing streams, and then these other major challenges here. And also mentioned that during the transport of this debit flow, it involves mass transportation. So the debit flow channel interaction can be quite challenging to really to understand and also to model here. And we call the typical term called entrainment. Entrainment means that this debit flow when it really goes through certain area, so the channel bed, these soils and the bank, the soils can be eroded and added into this debit flow. They'll change the mass, change the viscosity, change the momentum, and then also change the mobility here. Okay, and meanwhile, the flow itself will also have this size segregation, meaning that part of the particles can be dispersed and then deposited in certain part of this bank here. Okay, and in the end, the transportation will run out and then deposit somewhere. So those are the mass transportations that we need to take up when we do numerical simulation. And also, if you want to build any barrier, want to mitigate or reduce the impact, then we need to consider debit flow structure interactions. And then the interaction not only include the debit particles, but also the flow itself here, okay, with the barrier. And also, if we have a different type of barrier, as we are going to show later, flexible barrier, and then there'll be a in-barrier components interactions during this impact of debit flow here. And also importantly, any barrier either is rigid or it's flexible, and then the border impact can be a dominant effect that cause damage to this barrier here, right? And so the work is, I report here is my 3 PhD students working on this topic and over the years here. And then the methodology we have adopted to address these challenges is to use DEM. It's one method. DEM, basically we use that to simulate to simulate the solid particle and also structure components show later, and by solving them using this Newton's equation of laws, yeah, translational equations and rotation equation here. Okay, and also we use the computational fluid dynamics to model the fluid involved in debit flow here, and essentially CFD will be used to solve this continuity equation and a locally averaged Navier-Stokes equation here. And then we consider interaction between this DEM and CFD and to exchange the fluid particle induction forces here, right? And so the one way that we can do is in a so-called unresolved way. Unresolved means that the debit particle normally is smaller than CFD cell here, and then we consider important induction forces like a drag force. Drag force means that if the fluid and the particle they have a different velocity, and then typically the fluid will drag the particle. Of course, the particle will also have a reaction force to the fluid as well. Here, that's drag force, and the buoyancy is mainly due to gravity, and there's also viscous forces that we can consider that viscous force, the physics is according to the acceleration difference. If two fluid and particle, they have different accelerations, and this difference in acceleration will cause a viscous force. We can use certain mathematical description to describe it. And then we use the coupling of DM CFD and by using open form to solve the CFD part, and then we use the last DM to solve the particle motion, and then we use the CFD-DEM as a coupling engine really to exchange this interaction forces here. So this is unresolved. So unresolved, as I mentioned just now, that typically the CFD cell is bigger than the particle size. And indeed, from numerical experience, normally the CFD cell should be at least 3 times and bigger than the larger particles in the particle system here. Now let's look back this debit flow, the cell here, okay? And so this is the typical sketch of the debit flow here. So the debit flow is complex system, as you can see. You can tell that debit flow involve a large amount of water, and which makes them highly mobile, of course. But also the particle system is vastly different in terms of particle size. At the front, you have bigger blocks, can be 1 meter, even in some cases can be 10 meters big here. And then you have pulse debris, and it cause debris, and it can be millimeter and sub-millimeter, and also you have fine matrix, which can be in micron scale here, right? Okay. And then if we want to use a DM to simulate them, and then you can imagine that if you want to simulate such a wide grain size distribution, it's going to be very computational challenge, right? And let alone that if you want to respect their shape, and they'll add more challenges here. So what we do in the unresolved CFD-DEM coupling is that we consider this water and this fine matrix, fine bond, and then to consider them as a equivalent slurry, and then we're going to use CFD to solve them. And then we consider the coarse debris, the pebbles, blocks, and boulders, and then we use DM to simulate them as a granular particle system here. Okay. And then we consider the exchange of interaction forces between CFD-DEM, and in this way we can simulate a typical debit flow here. Right. And then, of course, I mean, when we develop a new method, we need first benchmark it, and then there are some analytic solutions that we can make use of, and then for benchmark here, and then, for example, first, and then the Stokes sedimentation is a benchmark that we drop a spherical particle and into a container here, and then there's an analytical solution provided, and then we can benchmark it, and then this shows a very you can see the particle when it's falling down from the air will have a near linear accelerations and to the peak velocity, and then once it's touch upon the water surface, and then the drag and other forces, interaction forces, will drag it slow until to certain depths it's going to be reach a so-called terminal velocity. And so this change of velocity can be predicted and is quite consistent with the analytical solution. Another benchmark is Tasaka's 1D consolidation that we can simulate a one soil column and saturated with water, and then do this simulation and compare it with Tasaka's 1D consolidation solution, and have good match here. And we can also verify that in other examples, for example, dam break, and then we have a container and then serve the dam, and then we pull out this door, and then let this collapse, and we can either consider the particle system, or we can use a pure liquid, and then we can also consider a mixture of them, and that served as a benchmark verification. Here, for example, we can verify the water with the particles mixture, and then if we replace the water with a Herschel-Barkley model, and their viscosity will be higher, and then with the particle and system, and we do another comparison, and then if we change it further using a Bingham fluid model for the CFD part, and then we could get different thing, and this served another validation example. A further validation we have done for this unresolved CFD-DEM is to benchmark it over a real case happening in Hong Kong, and this is called Eaton Road debit flow. And that is a very larger debit flow caused by single line slide source and triggered by the black rainfall. And then a debit flow cause this debit flow run onto this road and then block out this. This is the only road that are connect Hong Kong to the airport. Okay, so basically it's caused a major almost 1 day blockade of this road, and such that all the airplanes has been ready to delayed and canceled on that day here. Okay. So the debit volume is around 2,350 cubic meters, and runoff distance is 600 meters. And so this is the photo of that debit flow whole route here, and then we get this digital elevation model, and then measure the different part here, and then we further use DEM to simulate a topology boundary, and then we put a DEM packing of this south part, and this is going to be mixture. For that one, we also consider that according to the study investigation, that there are 3 locations along the transport route, and then it's erodible. Apparently, that the part of the scaly soil was eroded away, and then we provided 3 erodible bed and these locations to add up to the total volume distance that are from the south part with the deposition part here. We calibrate the model parameter, and also this erodible bed part, and we back analyze their model parameter for the simulation here. And so this is the erodible bed part that are shown that after study investigation here. Okay, here is the comparison of 3 cases that we simulate. One would be the first is a mixture, and then the middle one is pure slurry, is pure CFD simulation, and the right one is a dry erodible bed, and then we consider the pure DEM simulation, the dry one, and then we further compare their front velocity and versus change, means along the flow path that are, and we find that the mixture simulations really match their the observation pretty well, and the position is through some kind of like a people standing nearby of this site and took a video, and then from the video and the people basically doing analysis here. It's not from monitoring here, and then so that shows that we can use CFD-DEM coupling really to capture the real case of the validation case here. So the key part I want to show today is we can simulate debit flow, of course, and we can really choose different debit flow types. And the key part is for engineers, how we can really develop countermeasures to mitigate the impact of the debit flow here. And then in the past, normally people build the so-called check dam, build a concrete reinforced concrete dam or a concrete dam, and then shut down this channel, and then use that to be ready to continue to intercept a part of the debris flow and reduce its impact. But nowadays, the flexible debris resistant barrier has been very popular means here. Okay, and there are two types of flexible debris resistant barrier. One is called twisted wearing net barrier here, and basically you use like a steel wires and to twist them together and form a network here. And the other is a ring net barrier. And you can tell from this picture that we have individual high strength rings. And then we connect these rings together and using different kind of strategy. And then form such a network. And this network can be further reinforced by cables and by these columns to serve the as a barrier for debris flow here. Normally, this twisted wire it's only for small gullies and to try to really to resist the small scale debris flow. But this ring net barrier can be usually for larger scale and larger scale gullies mitigation measures here. Okay, it has been very widely used now in many places and in Hong Kong as well here. And then now let's look at how we can really simulate the flexible barrier. For the twisted wire net barrier, indeed we have done simulated by DEM here. This is a typical unit that we consider for this twisted wire things here. Okay, and then what do we do for this unit element? And then we consider by DEM, we lump sum all this mass into the particle as the nodes. So the nodes will carry all the weight. And so the bar will not carry weight, but it has a certain strength. And so the nodes particles will connect by these bars using a so-called remote interactions here. They can really have interaction forces, and then it can be broken as well here. Okay, so this is how we further extend our DEM simulation to simulate such a unit for wire knot here. And then this is how we lumped this T-squared particle with remote interaction for that purpose. And then we for each bond, they will divide by bond. The bond have certain kind of normal and shear stiffness, and they have tensile strength, shear strength, and also they have radius as well here. And they can develop certain elastic forces at the moment, and then have strength criterion, and it can be broken here, right? And so, but the interaction of this wire will mainly in our simulation will be interactive at this particle level here, at this particle level here. So the wire itself at this remote or vertical bond will be twisted by a neighboring of a particle in the DEM simulation here, right? So this is our consideration here, and then we can use this unit and to generate a whole twisted wire like this one. We can also use DEM to generate a cables like this here, horizontal cables, and this cable can really sliding over. This nets can sliding over these cables here. We can also generate a so-called single wire. Single wire is this thing here. This is a single wire, and this is supposed to be a double wire here. We can also make a difference about these fine details, and by assign different stiffness and strength for the remote bond here, right? So this is how we model this twisted wire here, and we can further calibrate this twisted wire, and these are some experiments, and they do this static test, and ready to see the deformation. We can calibrate them by generating identical wires, and then we compare their deformation and at different locations here. These are the calibrations for different cables here. And then this is our simulation now. we install such a twisted wear, and then we subject to a mixture of particle and fluid by CFD-DEM here, right? And so as you can tell from this simulation, there this is a typical simulation scenario that we can produce here. And then we just split this visualizations. The left side, we only show the particle system, and on the right side, we only show the fluid streamline. Actually, they are mixture here, right? That's for the visualization purpose here. So the key features that we can capture from this simulation is we see that a simulation can capture this inflow debris particle interaction. The particle itself, they can interact with each other, just like a dry particle system here. And also, the particle and fluid interact with each other in such a way that we consider CFD-DEM coupling. And also, the particle can interact with the barrier here, and fluid also interact with the barrier here. And the barrier, the net itself can sliding and stretching over the cables here, right? And so that is another thing in action we can capture for this simulation here. Okay, this is the side view here, and how when the debris flow coming down, and then it will be first intersect the coarse particle will be intersected within the barrier. Fine particle and liquid can go through here. And when this barrier is fully accumulated and then form a huge barrier, that is now the whole thing can reduce the permeability of things. So the much of this water will overflowing from the top rather than go through from the bottom. As you can see, there's reduced liquid flow from the bottom later on here, right? So that is the simulation can show here. And then we could also do quantitative analysis here. And for example, here, there we can really compare the total impact of force, and then compare the pure dry DM simulations, and also with our covered CFD-DEM simulations, and to see that the benchmarks and what a debris flow will cause. As you can tell, there at the similar levels and similar inclinations that are the mixture can generate much higher impact force than the dry particles here. That makes the debris flow more damaging than other type of fluid here. And also we can do a parametric study to see how this impact force change with the slope angles, like peak force changes, flux angles, what are the steady state forces, and then these are the other quantitative analysis that we can do through this simulation here. We have further quantified the impact, and the left side is published results by Leonardi and back in 2015, and they use a three-way coupling, use LBM coupled with DM for the couple MBM. LBM for the fluid, DM for the debris particles, and FEM for the barrier. So the coupling can be quite complicated, but we only use this two coupled CFD for fluid and DM for particles and barrier, and we can generate quite a similar trend. And then to investigate whether the impact force and how that changes with the incoming flow properties, like a solid fraction, how much particle percentage will do. For example, when it's become denser, the solid fraction increase, and we find that it can really approach to certain steady state impact force. Okay, and so that is from our CFD-DEM simulation here. The solid fraction will increase the peak force and also as well as the steady force. Okay, and that is for a twist wear. As I mentioned, a twist wear barrier, and then normally is only for a small scale simulations. But if you want really to have a real larger scale mitigation, and then normally in practice, people use this rain net barrier. Rain net barrier, as you can really, this is basically a assumed figure how the rain will be connected each other in such a strong way, right? And so these are the high strength rains, and then this will be further connected to with the top cables, and also you could really have a certain layer of cables to connect them together. They'll be fixed by some anchors and to this to the two banks here, right? And so this is form a major rain net barrier. And then for the rain net barrier, and then we could also use a DEM to simulate it. For example, this is as a demonstration. For each ring, and we can connect the particle together, use certain diameters, connect them together, and we can also we develop a certain shorter cylinder bond between the particle to form them together here, right? And then we for each run, and typically we in our simulation we use 80 to 100 particles here for each run. Okay, and also we can really to simulate the cables by bonding part together. And then at a certain part, we can even simulate the so-called energy dissipator. Energy dissipator is a special part of this facilitators and is basically can dissipate the impact, especially the big boulders, and effectively and reduce the damage to this barrier here, right? And then this bonded particle from rings, and the ring itself can be stretched highly deformable. As you can see here, this is just demonstration of the deformation. The ring can be deformed, stretched, and then the cable can also be deformed here. And so they have a strength, they can be broken. Okay, and this is a whole net, that whole ring barrier net, that ring net barrier that we generated, including this cable, 3 layers of cables, and a good number of these ring connect each other together here. Okay, this will form this ring net barrier, and then we need to do calibration or benchmark as well for each ring, and then we can subject to this the stretching here. Fix one end and stretch another, and there's some experiments test and also past results. We can benchmark with them here. This is a single stretching here, and also we could also to look at the energy dissipator. Energy dissipator we generally, and then we consider a trilinear parallel bond model, and which depend on different series, the velocity, and then we use that also. We calibrate by experimental test, and to really fit this experimental observations for this energy dissipator model here. We could further benchmark a single ring for different tensile tests. And this is like a 2-point stretching, and this is a 3-point stretching. And then there are also experimental results reported for calibration here. And then we want to further calibrate the overall system response. For example, if we form a ring net, and then it's subject to a debris impact, okay? And this is the simulation we benchmark a falling ball here. We drop a spherical ball and from the air, and then let it falling down to this ring net here. Okay, this ring net itself will be connected through some cables, and so the ring net itself can slide over this supporting cables here. And so this simulation just give an illustration, this so-called the curtain effect. For example, in your bedroom, and you have a curtain, and then you pull it under or close it, and then this whole thing will slide over this curtain rod here, right? And we can further compare the response, for example, the displacement over time, and with the experiment done by in this work here. Now we put such a rain net barrier along a inclined slope and subject to a mixture of debris flow impact here, right? And then the rain net itself, including the net itself, and also the energy dissipating part and the cables, 3 layer of cables, and also have this vertical left and right vertical cables here. And then this is the simulation that we have done, that this will impact to this rain net barrier, and the water and fine particle can go straight, and then the coarse particle will be intercepted, some can really bounce out, and then with accumulation of this one, and then a majority of this debris particle will be retained by this rain net barrier here. This significantly reduce impact to of the debris flow to the downstream infrastructure, for example. And this is the further realization of this the response of this rain net barrier subject to this impact here, debris flow impact. This is a side view of this barrier itself. As you can see, at first, the bottom part will subject to the front of this debris, and then it will generate deformation. And later on, with the further accumulation, the top part will be reinforced to sustain the load, and then become significantly deformed here. And this is a top view here, and of this net here. This is the front view that we see from the front, how the force can be transferred throughout this net, and then this further will be transferred to the cable. So the cable will be the major force barrier, and this cable will further transfer this force to this the bank, the anchor at the bank here. So this is how the force transfer mechanism works in such a rain net barrier here. This is the further sketch, recap of this snapshot of this the deformation. You can see here at the bottom part, their deformation is large, so somehow the rings can be so severely deformed and form even a nearly square type of the deformation on top, and their deformation is less, and then more or less still stay in the circular shape here. And so this is a demonstration of the deformation here. This is a further comparison of this how the rain net can retain the debris. This is a real picture for real rain net barrier holder after a debris flow impact here. Okay, and this is our simulation that you can see qualitatively, and they are quite similar. Also, the effect of these cables, this how can really to help really to form this so-called double bulge shapes, and for this retaining mechanism here, right? And so and of course, I mean, we can further quantitatively analyze how the different incoming flow features, like the float number, which is the ratio between the incoming flow velocity versus this under some geometric properties of this slope, and then we can really to quantify how the retained debris flow mass and proportion to the incoming flow numbers in such a way. We can also quantify the reaction forces in each layer of these cables, and then over the time of the impact here. We can also look at the energy dissipation ratios and over the different incoming flow with different photon number, and then to quantify the efficiency of this the barrier mitigations for this debris flow here. Now, this offer too, I just demonstrate some validation, some benchmark, and how we simulate a impact force for the barrier here. And so the tool itself can help us to advance our scientific understanding of this impact mechanism here. Okay, and for example, we have such a high fidelity simulation tool. We can extract the particle system to analyze their contact force network that showed on this left figure. We can also identify and separate the fluid part and then to impact the impact, and then we further analyze the combined effect here, right? And then we can also change the barrier geometry and also other properties here. And this is a quantitative analysis that we published in Geotechnique back in 2020. That we found that there's a K index can be used as a design index, which is the incoming flow head, and versus this barrier head. And that ratio is important design fact. Of course, it depends also on other like incoming flow fluid number and also the pre-impact velocity and the barrier property as well here. Okay, and then we change this the different ratios and use that and we can develop a quantitative relationship. And by far in civil engineering, they don't have a design tool to evaluate the impact of debris flow over a flexible barrier, and this will serve one of the first for that purpose here. We can also quantify many different parts and then to really quantify the different mechanisms here. And one thing is you can tell from the lab experiments and on the right simulation is this is a typical so-called pile up mechanism. Pile up means that the flex barrier will retain part of this debris particles and will hold it and accumulate it, build up in front of this barrier, and this will build up layer by layer until the fall, and then the following the further incoming flow, debris flow will overspeeding of the top. Okay, and so this is the whole process we can quantify and at each stage of how this pile-up mechanism works here. Okay, and this is a quantitative result that we can quantify, as I mentioned, that epsilon, the incoming flow head over the barrier ratio epsilon, how that in combination with the fluid number, and we can design some we can plot some design mechanism, design diagrams ready to use that to provide for the engineers for reference. You want to design certain flexible barrier mitigations. Here is again follow up this impact mechanisms here. They are essentially in debris flow study. They identified two impact mechanisms. One is called pile up. The pile up, as I mentioned, basically the debris flow will be retained by the barrier and then layer by layer largely, and then to fill up this barrier and then form overspeeding here, overflow here. And then there's another mechanism called runoff. Runoff is essentially when the debris flow impact on this barrier and then part of the retained, and then it will form a so-called circulation, and so roll back flow here, and then become circulated, and then until the whole barrier is filled, and then form overspeeding flow here. Apparently, the pile up and the incoming flow normally is smaller, and then the run up mechanism normally you have a very rapid incoming flow here. So this is a comparison that when we simulate two cases. One case referred to an incoming flow of 2 meters per second and form a pile up mechanism that's showed on the top here. And then if we change the incoming flow velocity to 4 meters per second, and then it will give us a run-up mechanisms. And then we can quantitatively analyze the two cases and to understand better what are the fundamental physics dominant them here. Okay, and for example, here this is give you a illustration how the pile up impacting works here. And then on the right is the contact force network, and then comes and also combination with this flow streamline here, right? And then so the contact force network and interact with this barrier is is in the pair up mechanism is totally different than run up mechanism here, right? And so also, for example, in certain places, if we design certain certain net barrier, and then we can really test using different incoming flow. And so, for example, in this case, and we test if the incoming flow is pure viscous fluid like a mud flow, or is a debris flood, and or is a debris flow with different solid friction, solid content, okay? Or we use a pure rock avalanche to impact it. And so we can really generate a different type of depth flow to test the performance of the same barrier, the net barrier, how would it perform in resisting the different impact here, right? So this is what we call augmented barrier here. Indeed, and now when we install a barrier at certain locations, we normally we want really to expect that it only receives one single type of flows here, right? And then we can also quantify the so-called the impact mechanism transition and what kind of parameter dictate the transition changes here. And then we can do a lot of parametric study and really to generate different incoming flow, and then with different barrier, and then this other diagram we quantity diagram that we generated from the study here. And it can be used really as a reference for design here. And other than flex barrier, as I mentioned, that traditionally there are many other rigid barrier. Also, is possible that we can make use to analyze to mitigate the debris flow. And here, for example, these are the traditional rigid barrier. You can use a concrete dam or a reinforced concrete to mitigate it. Okay, or for that the concrete dam, and you can really to provide some kind of slit gap in between, and this gap typically will allow the water and fine particles through, but it can really help you really to intercept the big boulders here. And then we can really compare the performance of this different design of the area, and then this will help us to really to choose the optimal design for certain locations. This is the further comparison that we can quantify the particle system impact with the barrier. Also, we can quantify the fluid part here, right? And so these all offer very detailed microstructure informations and help us to understand the mechanisms and also provide quantitative results and for possibly practical design here. And then before we make a break, and then I want also to introduce some further development of this coupled CFD-DEM. And as I mentioned that for debris flow simulation I just introduced, we use so-called unresolved CFD-DEM. And so the unresolved CFD-DEM is referred to this left. And where I mentioned that typically we use a coarse CFD cell, fluid cell here, and with the fine particles and particle size typically small and 3 or 4 times smaller at least than this CFD cell here. This is called unresolved here. Okay, and then meanwhile we have developed other different coupling scheme, and one coupling scheme is called fully resolved on the right here. So what is a fully resolved CFD-DEM coupling? It's basically we consider like even in the debris flow case, we have a case where there's a big boulder. The big boulder, the size is so big, right? And then if we want to fully resolve the interaction of this big body with the surrounding particles and fluid, and then we need to have final mesh here. So and this we have much finer mesh compared to the particle size, and then we need a fully resolved interaction. It's called a fully resolved here. Okay, and then there's a gap between this unresolved and fully resolved, and then for example, if our particle size is comparable with the CFD cell in that sense, and then we call it semi-resolved here. So we have fully resolved on the right and unresolved on the left, and semi-resolved in the middle. And but in the real situations, that is not like one method can suit all. For example, for unresolved, of course, their computational efficiency can be high because we have a cost mesh, and this fully resolved, the resolution is high, but the computational cost is very low here. And we have a special case of semi-resolved. But in reality, and then the best strategy is trying to combine the different components together. We call it hybrid resolved and semi-resolved CFD here. And we can use that, we can relate to describe a complex system. We have quite a wide range of particle size, and also especially for so-called gap-graded solid here. In that sense, unresolved still, and we use the previous coupling scheme, just different equation here. And for the fully resolved CFD coupling, and we can use a immersed boundary method, and then to fully resolve the boundary of the particle and fluid interface, and then to calculate the quantity. So that's something that is not shown properly. Sorry for that. And so essentially, we fully resolved this interface and get interaction between each individual particle with the surrounding a lot of safety cells here. And for the semi-resolved, the idea that trying to do interpolation, we use interpolation interpolation kernel function, and try to interpolate the interaction force of this particle with the surrounding safety cell in such a way to gain improved resolution here. And also the particle itself can, as I mentioned in yesterday's lecture, that we can use different modeling approaches to try to approximate the shape. For example, we can use a standard distance filter method to generate DM packing with quite a complex arbitrary shape. And then we can further now couple with CFD in different schemes, and then to the coupling can also leverage the GPU computations and for parallel computing. Yeah. And some validation. First, unresolved CFD for this case can be, we can use another example, is basically fluidized bed, and which is quite popular in chemical engineering, and we compare that with the experiments found here. And also for the unresolved, we can really use different traveling velocity for settling here, okay, and compare with experiments here. And also for the semi-resolved, we can really try that if we only use this like unresolved resolution is not enough, we further refine the cell, and to this cell, and then to this semi-resolved, and then by the end that this semi-resolved will give us a much better results to this one here. Okay, so this is another benchmark for this semi-resolved CFD-DEM. And also another benchmark example is we call it Ergens test, that we have pressurized the water fluid, and then to flow from the bottom, and then to the top, and this part we have a region of this particles and particle size, and the fluid cell is comparable, and this is some analytical solutions that are developed for comparison for this Ergens test here. This is the further benchmark for the fully resolved. And now we consider settling of this a non-spherical particle here. Here in this case that we this settling we make it perfect, and if it's not perfect, essentially this spherical ellipsoid particle is going to flip, okay, in a quite irregular settling process here. We can settle with different shapes and then to get this settling curves and compared with some experiments in the literature. This is another benchmark for the fully resolved, and we have a single cylinder of balls, and is we oscillated and then in a fluid here, and there are some experimental tests that are that's done that we can really use this fully resolved to see that how the impact of force. This is the match of force, and also this is the simulation results. As a move from left to right, and then the top, in front of it, you have a higher pressure, and behind it is generate a lower pressure zone here. Okay, and so this can really to switch and do in the different direction here. And this is a very seminal test we call the DKT test. We basically you drop two balls in there, let them settle in a container, and the ball at the beginning have a certain distance, okay, and then at the beginning this stage is called drafting, okay, and basically you're getting down here. But as I mentioned in the previous examples, and then when the ball settling in such water, and then in front of it get a higher pressure, and then you behind it get a lower pressure zone. This lower pressure zone will provide a less resistance for the top particle. So the top particle will develop acceleration than the bottom particle, and then they will kiss, as you can see. And when the top particle catch up with the bottom one, they will kiss each other. Once the cage generator impact, generator disturbance to this fluid field, and then this will generate a tumbling. Okay, and so this is typical DKT test here. Okay, and this is further that we let the two particles with different shaped sphere particle move toward each other or move away from each other. We can fully resolve their surrounding influence, surrounding fluid field in such a high definition view here. This is further example, probably in the cost engineering applications. We have fully resolved the CFD-DEM. Here the particle is non-spherical, so their shape is quite complicated. And then we have a water like waves and impact on such a granular pile served like in the coast area. We have this coastal armor protection, and this wave can really to carry out the particle onto move it from bottom to top. And meanwhile, the water will seep down through the pores at the bottom, and then some of this the air will be squeezed out. So this is a very high resolution simulation that we can do for this fully resolved CFD-DEM problem here. Okay, this is a further examples that we have this kind of like solid column collapse here. And as a comparison, we have a dry case, purely dry case, and then we have fully submerged case where the solid column collapse in this water, and we have a half-filled middle case as a comparison. As you can see that the collapsing distance or runout distance is different in the three cases, and also their interaction with this water also exhibit quite different features here. And the last example I want to show a example of this hybrid resolved and semi-resolved CFD-DEM problem is called a diffusion problem here. And then in this example, we have incoming flow is a mixture of a fine particle with water. Okay, and then the particle is non-spherical. Okay, and then but the size is very small, and then we have fun part. We can use this semi-resolved CFD-DEM for that modeling, and also it's gonna be this incoming flow mixture will go through a cos matrix represented by this non-fat particle as well here, but their pore is bigger. It can allow the water go through, and it can also allow some of this fine particle go through, but it will trap part of this fine particle. This is what we call a blockage, and sometimes also people give a name called diffusion here. This is the assimilation results. On top is purely fluid flow velocity field of the streamline. Okay, and then as you can see, at a certain part, when the pore size of the throat is narrow, and then it really generates this high pressure field here. Okay, the flow can be kind of complicated. And the bottom is the particle system, how the fine particle can some of them can go through it, and then the others can be trapped, right? At the fun part because their matrix structure in the port here. Okay, we can further do a variation for this cos particle case, and we compare it with a sphere case where we have pure spherical particle for fines and matrix. As you can tell that compared to the top part, and then there'll be very small number of fine particle will be trapped and by when they go through compared to the top one here. But now if we change the particle size ratio, we let the coarse particle and the fine particle their size ratio reduced reduced to 5. Okay, and then you can tell from this bottom case, and because that ratio reduced, and so the pore and then there will be a significant number of this particle will be trapped at the final part of this matrix here. So that is how we ready to tackle this the coupling of this problem here. Well, for a wet line, in that sense that you probably one way that you can relate to add a very viscous fluid and to simulate it as a mod line, and then use the tractor and wheels to simulate this wheel modeling action. And because as a mod, and you don't normally encounter a lot of particles, and so that is my suggestion. You can use either FEM or CFD to simulate that purpose, right? And if you want to use a DM and interact with the tractor, you can use pure DM, but use DM to simulate a mod, and then that can be changed in a way that you need to add some bond in certain places. But I would say that probably it's a more you can use a highly viscous fluid model, and then using CFD to simulate this muddy line here, and then but for CFD-DEM, typically in that sense, unless that you have a mod that makes with a major particle system, and then you can really consider that one here. So the second question is a lumped DM particle with the remote induction method applied to maximum stress criterion, both normal and shear to a size bound feeder. However, real material often show more complex feeder behavior, such as progressive damage or plasticity rate factor, which are not addressed by the simple stress criterion. How can this limitation be addressed in simulation? So as I mentioned here, our lumped discrete particle with remote induction, we only use that as a simplified way to model the the VNet, the twisted wire network here, right? That serves as a just simplification, but that is on the individual unit levels, and on a whole structure levels, you still have a like a progressive failure. You have other effect, and so that is structure response. Of course, I mean, as I mentioned, that beginning, and this is a simplified way to really simulate this twisted wire, and you can further develop or refine this model to capture what's so-called progressive failure, and then but of course, I mean, this is a trade-off between the resolution with the computational efficiency, and it can be addressed, but it really depends on what benefit you would prefer, is computational efficiency or accuracy, or you want to have balance of it. Okay, in a sense, DM indeed can help you really to capture whatever of things, and you can really to specify a more advanced model to describe this how progressive damage in a bond developed, right? Okay, and you can really use certain kind of like model to describe the plasticity, viscosity, and the viscoplasticity to address the rate effect here. Okay, but I mentioned that for the twisted wire simulations, and we just did a approximation and simplify the problem because the wire network itself is big. Okay, so at the unit levels, and we want our model as simple as possible. But collectively, we can capture the collective behavior of the structure response of a twisted wire barrier when subject to this debit flow impact.